Firstly, it gives me great pleasure as the CEO of Portsmouth Water to introduce these next two speakers who are going to be talking about the challenges of locating leaks on plastic pipes. Our network in Portsmouth Water is about 50% plastic, which is surprising, as it only seems like yesterday when we started putting it in. But anyway, that just shows how old I am and how long I've been around in the industry. So yeah, I'd like to introduce Alex Barter, who is a director of Barter for Things, which is a relatively, I say not brand new, but a few years old startup business focusing on Internet of Things technology, amongst other things. And also Jamie Jones, who is our Leakage and Smart Networks Manager at Portsmouth Water, and dealing with all things smart and leakage and innovation related. So great to see both Alex and Jamie on the platform this morning, and they're going to talk about some work that we've been doing in Portsmouth using IoT technology and pressure data to try to improve the way we locate leaks on plastic pipes. So Jamie, Alex, over to you.
Well, thanks, Bob. I'm still waiting for Alex to arrive on the screen. So Alex, are you there? And
Hello, Bob and Jamie. We're just trying to find Alex, and we'll bring him to you as soon as we possibly can.
Okay, that's all right. Well, as always, I've got a backup, and so I can start talking while we are waiting for Alex, and I will share my screen instead. So here we are. Bob, can you see my screen? Good, excellent. Thank you, Bob. Thank you. So, okay, and while we wait for Alex to come in, I thought I would start by introducing myself. I'm Jamie Jones. I'm, as Bob said, the Leakage and Smart Networks Manager at Portsmouth Water, and I will be joined by Alex Barter, who is the Managing Director of B4T. Over the past few years, Alex and I have been collaboratively developing an IoT pressure sensor that has lowered the cost of pressure logging. This logging is primarily developed to fulfill the regulatory need to have a pressure sensor at the average and critical point in each of our DMAs. But with budgets are very tight and plenty of DMAs with no signal, these low-cost IoT pressure sensors became the most cost-effective solution for dealing with this issue. This project was very successful and got us thinking about how we could utilize these sensors for more, and in particular for leakage detection. The result of this was a practical IoT, and it's what this presentation is about. And the result is really an alternative way of finding leaks on plastic pipes that will reduce the runtime of a leak from about a week on average for us at the moment down to a day. So at Portsmouth Water, as Bob has just said, we've always had a very strong mains renewal program and taking it very seriously, historically renewing around 1% of our pipes a year. This has meant that we're actually up to a position now where we have, as Bob said, 50% of our network plastic. Now, I need to tell the Leakage Conference that finding leaks on plastic pipes is very difficult. And these traditional techniques have normally been very costly or have returned a large number of false positives. At the moment, Portsmouth Water conduct a large number of step tests on the network in these areas of plastic pipes, and as well as being costly, these can lead to customer interruptions and flow reversals and an uncalm network, and so it's not the most ideal solution. I therefore set Alex and his team the challenge of using the IoT loggers to come up with a solution that returned better results for us and were more cost effective. So yesterday I spoke with Robin Bell at Informatics about the benefits of calm networks and an automated network model. In his presentation, he talked about the PALM model And the digital twin is a key objective is to take the calming of the network to prevent that. That's the P in the palm, prevent leaks occurring, while also providing the secondary benefits of the awareness and location. Practical IoT flips this round. The aims here is to find leak quickly, so to lower our awareness or A in the palm, especially on plastic pipes, and also help with the location of those leaks on the plastic side. So it's about the A and the L in Jez's palm model. So practical IoT and digital twin for us are combined with the fixed noise logging of metal pipes that we've also done over the last few years, provide the kind of free solutions for us that are going to help us reduce our leakage over the future. So why is it important that we have new detection methods and new awareness methods of leak detection at Ports of Water? Well, people have come to me recently and said, you've done great reduction over AMP6, why don't you just carry on doing more of the same? But the fact is that we actually threw the kitchen sink at leakage over the past few years, and this reduction therefore came at a considerable cost, and this cost is very unsustainable in the long term. Well, yes, we have managed to get our leakage down, but in recent times it has now flatlined at this lower level and has been the same really since the start of April 2019, as we've had to scale back on the amount of money that we have spent on it. But of course, to achieve our 50% leakage reduction target by 2050, we actually need to reduce leakage much further. There is no kitchen sink that can be thrown at this time, and really there is no magic money tree available. Unsustainable costs will lead to unsustainable results, and either that means either spending too much in this area and underspending on other areas, or not achieving our goals. We therefore have to be smarter in order to progress. And at this point, I will pass over to Alex, who is far smarter than me, and go into the details of what IoT really means. So,
yeah.
I'm going to stop sharing and let you share now this time.
Great. Thanks, Jamie. I don't know if I'm smarter than you, because clearly I couldn't use the the Hop-In app particularly well, but here we are. Okay, so you might be forgiven for thinking this is sort of like a strange game of Guess Who. They've got glasses and facial hair and so forth. Right, I'm going to pick up from where we were. So, bada bing. Hopefully we've got some slides, yeah? Okay. So, Jamie, can you see the slides okay?
Yes, they're just loading now, Alex.
Brilliant. Okay. Well, it's clear what keeps Jamie awake at night, and I think probably BT's bandwidth to the office is keeping me awake at night. Anyway, so Jamie's set out a challenge. So challenge accepted. So when we got a challenge, we think about the solution. I was revert back to my my triangle of truth. How can we solve things, better, cheaper, quicker, so on and so forth. So we've got some critical success factors in and around working in plastic to certain levels, making sure that we're timely in what we do, but also back to the no magic money tree. We've got to be thinking about the pound in our pocket. Now, the headline of the presentation is around IoT data, and it is IoT data that I major in, that I can comment more about. But on top of the IoT data, which has to be good, it has to be the right ingredient, we tried different methods of cooking this data in order to hit these critical success factors. So I am sure that Tom over at Royal Haskellning and Stuart over at SME will wax lyrical about AquaSuite and about the SME products. So just to put in a picture of our approaches. So one way of cooking data is to use a machine learning platform with a hydraulic weighting in. A second method was to use people and expertise with some automated hydraulic analysis. And then the third way was homegrown from B4T, who know zero about hydraulics. So we just went with pure machine learning. Now we can sort of typecast where these different data solutions would sit in terms of their quickness, goodness, and cheapness, as it were. The reality is these things are a lot closer than you think in good ways. So back to the point that I think I probably made, John. So you have to have a decent ingredient. You have to have good data. So we've deployed extensively with Portsmouth over the last 3 years IoT sensors using the 0G stack from Sigfox. So this represents like a new sort of boundary in how we collect data. It's ultra lightweight. It's low cost to implement. And what I thought I'd do with this presentation, I'm going to come back to it in a bit, is to kind of talk a bit about IoT in terms of that real how you implement it, because it's much discussed, but I'd venture little understood. Anyway, so going back to this particular project, so we've got 10 of these IoT sensors in and around a DMA in Portsmouth. We simulated bursts by performing flushes and so forth, and the results were consistent. So I've got a map here with the AquaSuite software, and the two yellow stars are where we've got the nearest pressure points. Up to the top right, we have the machine learning platform that we built in B4T. What we've done there is we identify periods of significant change in flow, and at the same time we're performing machine learning every 15 minutes on all of the pressure devices, and we look for the most significant drops in pressure.
Alex, can I just stop you there, because I think the slide you're trying to show is it's taking a time. I think it's just loading up now. Yeah, I think we got it now.
Oh, sorry. Okay. Sorry, Bob. Okay, so the slide I'm on now, which says "and verifying manually," this is the analysis from our friends over at SME, so Stuart and Rashid, and same thing. They nailed it as well. So we've got the same results. So 3 different approaches, all in their own way, all achieve the same results. So, IoT data got to be good, and then we have we have our scope to deploy. Now, we've made a good start. So where do we go next? How do we take this to scale up? So there's 2 parts. One part is better mathematics. What can we do with the approach we have to optimize the data? So for instance, there's an approach to encode the hydraulic model as what we call a directed graph. There's a second approach to improve our machine learning modeling by using tensors or artificial neural networks. And then there's a third approach, which is to look at feature extraction by converting time-based events into frequency-based events to extract salient features. So that's in the maths. Now, open hand I shall play here. My maths at A level wasn't massively successful. So I look at more at cost benefit. So my job is to now drive down the cost of the data point so we can start to scale this up, to achieve full roll out across entire water company operations. So I'm going to take a little bit of a sideways jump and, let's say, talk about the implementation of IoT in that sort of detail. Like I say, much discussed, but little understood. So what I want to do is take the concept of IoT, what is it that challenges us, and how is it that we crack those challenges? So what I've thought about is something that we're all used to. So noise, maybe a little less these days as as things are in lockdown, but noise. We're going to use this as an analog to understand the challenges around IoT. Leaves, dogs, and motorhead. Okay, so on this slide here, hopefully this is loaded up, I've got 2 bars to the left, and I've got a photograph of something that looks like a pipe that would come down from the toilet. That's a boundary box. So let's explain what it is that we're looking at and what analog we're using. So we want to understand, what is it about IoT that is special that makes it applicable for water applications? So let's think about sound, something that we understand. Now, to the left, I have a range of things that go from very loud at the top to very quiet at the bottom. And you'll see a little symbol, dB, that's decibel. So sounds are described by decibels. The next box along is radio waves. And again, slightly different, but still it's described in decibels. So let's think about sound. So the human ear can detect between around about 20 decibels up to 120 decibels. Okay, that's a dynamic range. So we can hear things very quietly at 20 dB as a whisper, and then up towards 100 dB as a loud rock concert. Then up to 120 dB is where you sustain damage from standing next to a jet engine. And then right at the very top, the loudest thing ever recorded was Mount Krakatoa exploding in the late 1800s, which was 180 dBm. So we've got sound. Sound has got a dynamic range. Now into radio, and this is where IoT lives. This is the challenges that we have to overcome in IoT. Your DAB radio will operate round about minus 70 dB. That's tiny. So your radio will pick up tiny amounts of power in order to deliver your 6 Music or Planet Rock or whatever. IoT exists much lower down. So IoT is in this dynamic range, round about minus 90 to minus 150 dBm. Tiny. So even though we're working in a small dynamic range, let's have a think about our physical challenge. Now, if you look to the photograph on the right, this is a boundary box. So this is what houses smart meters, also pressure devices and water quality sensors all over your estates. So there are things that suppress our dynamic range. So one thing is having a lid with metal in it. That normally gives us somewhere between 10 and 15 dBm of loss. And then as we go down, we can lose anything up to 20, if not more, dB. And when you compound that, I hope you're all still following, we're down, right down to the equivalent of hearing a leaf fall or something that only a dog can hear. So IoT is in these extremely challenging radio environments.
I'm going to have to move you along a bit, Alex, because you're running out of time. So,
fine. Last slide, Bob. Last slide. Scout's honour. Okay, so in order to meet these challenges, there's a couple of things we do. On the left, we're building smarter, much more highly acute listening equipment in the IoT realm. So the radio's listening better. And on the right, we're bringing in new devices that transmit with much more pinpoint accuracy and better power transmission ratio. So here we go, right at the end. What are we going to do? You'll hear more about jellyfish and smart metering very, very soon. And my job is then to bring that into the world of pressure, so we can then, you know, roll this out and meet these pressure demands. And that's it. Finished.
Well, that's a really good speed up, Alex. Thanks for that. Anything more from you, Jamie, or shall we move on to questions and answers?
So obviously, Alex, you there's a slide in the middle there that kind of got frozen. So I just want to kind of emphasise on that point. So it is very similar, as you say, to presentations that were given yesterday, in that the idea here is the pressure sensors are localising down into an area. So it's where these leaks are, and so it's using the pressure, and it's using the differentials in pressure between the different sensors that are out there. And the difference that we have compared to what was said yesterday is purely a different sensor logger, and Alex is using a different technique in order to get there. But it's the same principle as what was done yesterday, explained yesterday by both Daniel and also by Stuart. So yes, it does look like we're all on the same page, and it very much is that we're all looking the same way. And I think the key thing that Alex pointed out is that all these different solutions, they all have their benefits, and they could all work in different ways in different areas. And I'll stop there.
Okay, that's really great presentation from you both, in spite of the technical challenges at the beginning. A great recovery there. Thank you. Well done, Alex. So there's a few questions there on the chat, which maybe we can kick off with. So Adam Smith is talking about, maybe for you, Jamie, how what leakage runtime that we're talking about here. How do we know what the runtime is before we have realised there's a leak there? I suppose that's the crux of the question. So you talked about a week. What is that week that you're talking about?
So we're quite fortunate at Portsmouth to be quite a small area. And so what that means is we can look at the night lines of every single DMA that we have in great detail. And so in calculating the average runtime of a week, this has been done by a mixture of myself and consultants as well, in looking at the changes in nightline from a minimum level as they increase. And then taking in all the data and all the information that we have around how long it's taken our guys to go out there and find these leaks. And a lot of this work was done back in 2015 and 2016 in preparation for the fixed noise logging and work that made a big difference in 2018. You saw on my graph with that big reduction in leakage. But it's the same principle for the plastic side. The guys beforehand were going in and looking for leaks, and it was taking an average of a week in order to find each leak. And what's probably worth putting in the contents is that for us, our DMAs are much larger than most other water companies. They're averaging somewhere around about 10,000 properties. And so when I do give an area to a leakage tech, and there's certain areas in rules that are very large, I can see that them just looking at me with deathly stares and daggers as I've given them this huge area to look for leaks. And as we reduce leakage down, and as again spoke yesterday, we start going into these areas much earlier and before they've risen too much. They are looking for small amounts of leaks in much larger areas, and they need all the help they can get.
So what you're saying is that potentially, you know, we had a revolution a few years ago with noise loggers, which are now being deployed in large numbers and are very helpful in general for iron or metallic networks. This could be the next best thing on plastic networks, the mass deployment of pressure rather than noise, yeah?
Yes, very much so, yes.
So kind of combination of questions here. Ben has mentioned, you know, what do we need to do to accelerate the development of the sensors? I mean, and I'd like to add to that, Alex, what are we talking about in terms of cost differential, ballpark? You know, what is...
Yeah, I did cheekily reply to Ben. Yeah, there is cost to design, for manufacture and all this sort of stuff for sensors. So historically, for us, bringing an IoT device to life, capital spend is around about 35 grand. So that's in designs, certification, testing, so on and so forth. Sorry, that's a pretty straight answer. That's what it is.
Yeah, but in terms of my question, what I was getting at, Alex, was can you give us an idea of, what is the difference in cost, broad ballpark, between the low-cost pressure sensors, the low-cost equipment that you've been deploying here, and what it would have been previously, for example?
Yes, absolutely. So we understand that the market rate for GSM loggers is for around 300 quid, maybe 400 quid. And in the IoT domain, where we are looking at single purpose sensors, we're down at around about £170 today. But like I say, my mission is to get that below £100.
Right. And another question there from Stuart. How is this different from NB-IoT, which is kind of used elsewhere?
Yeah, sure. So I'm personally up for using NB-IoT when conditions are correct. So there are two things that we need to get over the line with NB-IoT. Primarily, it's the supply chain of the radio modules. So other flavors of IoT like Sigfox or LoRaWAN, we understand the power consumption well. And in NB-IoT, at the moment, it's significantly more. So we're waiting for that to come down. And secondly, on the network, I think Paul asked a question earlier about, sort of putting new infrastructure out. Always, you'll need to put new infrastructure out. Doesn't matter whether it's NB-IoT, Sigfox, or whether it's the GSM network. It doesn't matter. There's always a need for more infrastructure. With the likes of Sigfox and I guess LoRaWAN, we control that infrastructure. Less so with NB-IoT today. Whether that will change or not, who knows? But certainly, the second part of my answer to Stuart is control over the network infrastructure as well.
So, Bob, I've got an additional point on that. So I have spoken with NB-IoT and the people who supply that, and the issues are very much in the rural locations. It's a cost benefit of deployment. It's much easier to deploy where there's lots of people. But unfortunately for water companies, there's a lot of our assets are in very rural locations. And this means that there's very much a gap in the market at the moment, or a gap in the market, to Alex would use, an issue that we need to solve in the water company in these areas. And Sigfox came out easily as the kind of best solution in these very, very, very poor signal areas. It's also worth noting on the battery life. That is a huge part of the cost benefit for us. That was around the pressure sensing. The batteries are far cheaper and don't need to be replaced, or if they do, and they are very, very much cheaper than the ones already out there at the moment and needed for the other types of loggers. And so in doing a cost benefit, it's all about the whole life costs of loggers is where this even stands out even more as the kind of right solution for us anyway, with our challenges.
Yeah, I mean, I think just picking up on Paul's question there, did we install any additional infrastructure for the Sigfox? The answer is yes. We created a network, I think, isn't it, in simple terms, using our existing sites to facilitate those installations. Sorry, I'm just going to move on because there's a whole load of questions here. Really cracking question here from Glenn. How is the IoT kind of development changing the economics of managing leakage compared to standard approaches? This is down to the fact that we're spending less time finding the leak predominantly, I think, isn't it, Jamie?
Yes, yeah, very much. So because the sensors are cheaper, it means that we can deploy more on the network, and therefore you're looking at finding leaks in a much smaller area. These pressure sensors can also then be used for a range of other application, including the digital twin that I mentioned yesterday. And so what it's doing is it's really making things like digital twin and step testing not needed. So making digital twin far more cost effective and step testing not needed. And step testing is a very expensive way of doing leakage detection. It only just works out cheaper than just going out and looking for leaks. By the time you take in overtime and the chance that leaks could be spread out a bit and things like that. So, and all the planning involved. So very quickly, step testing adds a lot of extra burden. And by doing this, you're very much changing to having this data coming in every 15 minutes, leaks coming through every day. And so therefore, you're also dramatically reducing that run time. And so therefore, it's a case of finding leaks much quicker. And so you're just doing a lot more of what you're doing, but a lot quicker. And that's where the economics start to really change. It becomes cost effective to do this.
And is it too early to go into Louis' question there? Is it too early to see impact on DI at the moment, or is it because it's still relatively in its infancy, isn't it, in terms of deployment?
Yes and no. I would say DI from a smart metering side, there's certainly stuff there and it can be done, but it is quite early in that smart metering world. But obviously, other companies have done a lot of work in smart metering. From a leakage point of view, this summer there was, unprecedented demand on the network, and if we had leakage up at the higher levels that we had back in 2017-18, we would have been really struggling for water in certain parts of our patch. But because leakage was lower, that gave us the additional headroom. So DI includes leakage. And if we can reduce leakage as we have by 10 megalitres a day, and we're going to reduce it further over the next period, then that does obviously reduce a DI and gives us that additional headroom needed for these peak demand periods.
I think we're going to have to draw the session to a close there, guys. So, I think you can tell how interesting the session has been to everyone by the questions there, many of which we haven't had time to answer. But I think there are other ways that people can pose their questions through the various networking mechanisms available. So thanks to everybody for all of those questions. Really interesting stuff and a great start to this morning's session. And it remains for me to thank Alex and Jamie. Alex, for a quick recovery there after a bit of a technical glitch. So well done for that. And virtual round of applause from everybody. Thank you.
Cool, thank you.
Thanks very much. All the best, guys. Have a great one.